I'm here at Cubert to meet with their CEO René Heine and to learn more about their hyperspectral cameras. Could you briefly introduce Cubert as a company?
Yeah, sure. Cubert is a manufacturer of hyperspectral cameras, and we focus on video cameras mainly.
What originally inspired the founding of Cubert?
Yeah, originally the inspiration was that I was working in a development project and we started to apply for the FDA application, which is a tedious process. And there I decided I want to have my own company. And we took part of our development and founded a hyperspectral company out of it because it sounded more fun.
For those unfamiliar, could you explain what hyperspectral imaging is and what sets your approach apart?
Yeah, definitely. So hyperspectral is, as you see here, this is a live hyperspectral image. You see over there, it's looking like a normal, regular image of a regular camera. But the difference is you have in each pixel of this image one spectral response. So from, in this case, 400 to 900 nanometers. And in this spectral response, there's a lot of information about the chemical composition of the material.
What are the main technological challenges when developing a hyperspectral camera?
The biggest challenge definitely was the resolution. So we finally reached, this is now a megapixel hyperspectral camera. So 1 megapixel spectra in one image. In the beginning, we started with 2,500 pixels, which is just like an icon of your computer. So you don't see much, but for the beginning it was enough. But we really needed to get some resolution like that to really get into very interesting applications.
Could you describe some use cases of your camera?
Yeah, typical application examples for us is medical imaging. So we do Alzheimer detection with this kind of technology. We do a lot in industrial applications, sorting, quality control and such. Remote sensing for us is very strong, but also defense, detecting friends and foes from an UAV. These are our basic applications we pursue.
What is the most unusual use case you encountered so far?
It's a very good question. So first of all, right now we are preparing one camera which goes to Antarctica, where they want to put the camera underneath the ice in an ancient sea, which is still not frozen, and measure the flora and fauna there with the hyperspectral camera. But what I really enjoyed was this customer who had these dancing spiders, and they do some fancy dances when they want to attract the female. And so he wanted to measure the change of color on these dancing spiders with a hyperspectral camera. I think this is one of the craziest I've seen.
So mating ritual of spiders.
Mating rituals of spiders, yeah.
Do we have footage of that?
No, but no, I unfortunately don't.
So you mentioned Alzheimer detection. How does that work exactly?
We couple a camera like that with a typical ophthalmoscope. So when you're a bit older, you go to the eye doctor to check your eyes for eyesight, typically. And what we do is we attach a hyperspectral camera to this ophthalmoscope, and while you detect your eyesight, it measures the background of your retina and can detect these plaques, which are also visible in the brain. And this is a very good early diminutor for Alzheimer's disease.
Mm-hmm.
Yeah.
And what are other medical applications?
Perfusion of blood is a very common one. So measuring how good the blood perfusion on your skin is, in burnt wounds, or in surgeries. When you couple a hyperspectral camera with an endoscope, you can distinguish different type of tissues. You can distinguish arteries and veins. You can distinguish muscle, fiber and other tissues from each other.
Your cameras are specially suited to attach them to drones. Could you give some application examples of using your cameras with drones?
Yeah, this is basically because that was our founding. So very, very early after we founded this company, our first camera was that big, was 3 kilo heavy. And then there was this crazy professor, Mr. Barrett from Cologne, and he wanted to have it on a drone. And so he asked us to shrink it down. And so we put it on a drone for remote sensing. And that was an immediate hit, this camera, because there was nothing like that at that time. It was 2013, right? And so that's the reason why we are pretty strong on UAV usages. The reason is what you do is you fly a camera like that and you generate georeferenced map of your agriculture field, example given, or of your plot of different grass specimen, where you try to find the best specimen. And this hyperspectral information gives you information about nitrogen in the crops. It gives you information about the water content, about the water need, about the growth potential. You can predict the harvest, and this is a huge field, and it's still probably 50% of our business year by year.
And this is used in agriculture by farmers?
And no, typically this is in research. So the step to the farmer still is a bit too complex. So we're still moving towards making it DJI-like, which would be the appropriate complexity for a farmer. But right now you need a professional UAV, which is a big one, and this is already not 100% easy to fly.
You talked about defense applications. Could you elaborate on this?
Yeah, defense applications. I cannot tell most of it, but one application which we can talk about is friend and foe detection. So what we do is we measure specific invisible colors, which you cannot see with your own eyes. And they are very complex, so they can have a very complex signature, which is not easy to replicate. And the camera immediately detects if it sees a color like that, and then you can 100% be sure this is your camera and not an enemy. And this is one example we have in defense. And then you can combine that with a UAV.
And well, you explained the technology. So now here you have a sample camera. Could you just show a little bit how it works using these objects here?
Sure. So first of all, what you see here is it's looking like a regular camera. It's even connected with a USB connector just to a computer, and what it gives you is a normal image. I can crank up the frame rate a bit. So you would not, if you don't know, you wouldn't see that this is something different than a normal video camera, just doing images. But what you see here, in fact, is a spectral camera. So each pixel here gives you a spectral response. And from the purple, you get a very different spectral response, and you can see the chromophores in this one. And this gives you the opportunity to measure specific things. First of all, you can not have a boring RGB image. You can have a different view of the spectral data. I don't have grass here, but you can measure chlorophyll content, you can measure blood content, or you can train a very simple classifier to detect something. And I just trained a classifier to detect this invisible ink, which I have on my hand, and it should now light up.
Oh, okay.
This invisible ink, and this is basically what you can do with this kind of technology. And what it does is, this patch, being not visible to the human eye, has a slightly different spectra to my hand, like that. And so this is now calculated by the computer, and you can detect the marking like that one.
How do the Kowa lenses contribute to the overall performance of the hyperspectral camera system?
So first of it all, we have very high quality needs for these kind of cameras. We're talking very much scientific cameras, so the customers expect perfect quality, and Kowa delivers that. We have different needs than other camera manufacturers, since the systems do not work only in the visible, what the human eye can see, but they work from the UV to the near infrared. And we need partners who can produce lenses which cover this whole huge range and still have a very high quality of the image, and also high numerical aperture. And their Kowa lenses are quite outstanding for us.
What innovations or new directions are you planning at Cubert?
Basically what you see here, this 1 megapixel hyperspectral camera, that was the vision we had when we founded the company. So this is what we always envisioned, a video camera which is just like any other camera but giving you a spectra on each pixel. And now we achieved that. Still the cameras are quite expensive. So this is at the moment not for everybody. And the direction we are pushing very hard right now is to bring this technology to a broader market, bringing the prices down to normal industrial cameras. And it's basically miniaturization and cost cutting to have broader applications with these kinds of technology.
Where do you see the greatest potential for hyperspectral imaging in the next 5 to 10 years?
For us, 100% medical imaging is the most interesting and also most exciting field. So the reason is, right now we are just at that point where our technology is affordable enough for medical applications, which can be a bit more expensive, and giving the quality they really need to detect different disease in different scenarios. So that's 5 to 10 years, but I'm 100% sure we will compete against RGB cameras lately after. So wherever your RGB camera is quite not good enough, you might tap in more information that Hyperspectral can give you. Think about it like that. Every camera on the world right now is built just on the fact the human sees red, green and blue. This is totally arbitrary, and the light spectra gives you so much more information, and we don't measure that. And for me, this is an untapped potential for better quality, better decisions, better robotics in the end.
Mm-hmm. So what would you say is your vision for Cubert for the future?
Our vision is to make it affordable and make spectral imaging as normal as RGB imaging is today. Just if you remember, I still remember in the year 2000, RGB imaging was used in some crude industrial settings, and the consumers really didn't use it that much. And nowadays, everywhere are RGB cameras, digital cameras, and we want to bring the power of hyperspectral to a very broad audience.